Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we'll continue our look at wireless LANs. In the previous video, we looked at various fundamental concepts of wireless networking. But in this video, we'll look at some more specifics. Specifically, wireless architectures. By architectures, I mean how the wireless network fits into the greater picture of the network as a whole, including the wired network infrastructure. We'll cover exam topic 1.1d, access points, 1.1e, controllers, as well as 2.6, 2.7, and 2.8. Here's what we'll cover. Before covering wireless architectures, we'll take a quick look at 802.11 messages and the 802.11 frame format. 802.11 wireless LANs function differently than 802.3 wired Ethernet LANs, so there are some unique message types, and the frame format is different as well. Then we'll cover different wireless access point architectures: autonomous, lightweight, and cloud-based. Finally, we'll look at different wireless LAN controller deployments. We didn't cover WLCs in the previous video. They are used to centrally manage and control access points, and are essential in large networks, which can have hundreds or even thousands of wireless access points. Make sure to watch until the end of the video for a bonus question from Boson Software's ExSim, the best practice exams for the CCNA. So let's look at the 802.11 frame format first. As you can see, it has a different format than an 802.3 Ethernet frame. 802.11 frames are more complicated than Ethernet frames, but for the CCNA, you don't have to learn it in as much detail as the Ethernet and IP headers. So I'll just provide a high-level overview. First of all, there are many more fields in the 802.11 header than an Ethernet header, but depending on the 802.11 version and the message type, some of the fields might not be present in the frame. For example, there are 4 different address fields, but not all messages use all 4 address fields. Okay, let's look at each field briefly. First, frame control. It's 2 bytes, 16 bits in length. It provides information such as the message type and subtype. I'll talk about the different 802.11 message types later. Next is the duration/ID field. As the name implies, this 2-byte field has a few purposes. Depending on the message type, it can indicate the time in microseconds the channel will be dedicated for transmission of the frame. Or it can be an identifier for the association, the connection between the wireless client and AP. You could say that this field is similar to the Ethernet type/length field, because it has 2 different purposes. Next up, the addresses. Up to 4 addresses can be present in an 802.11 frame. Which addresses are present, and their order, depends on the message type. The 4 addresses that can be present are the destination address, DA. This is the final recipient of the frame. The source address, SA. This is the original sender. The receiver address, RA. This is the immediate recipient of the frame, but not necessarily the final destination. And the transmitter address, TA. This is the immediate sender of the frame, but not necessarily the original sender, the original source of the frame. Having 4 addresses like this isn't necessary in a wired Ethernet network, but 802.11 wireless networks have unique requirements. The next field is sequence control. It's used to reassemble fragments and eliminate duplicate frames. Then there is QoS control, which, as you probably guessed, is used in QoS to prioritize certain traffic. After that is a field called HT, High Throughput Control. This was added in 802.11n to enable high throughput operations. I didn't mention this in the previous video, but 802.11n, Wi-Fi 4, is also known as High Throughput Wi-Fi. And after it, 802.11ac, Wi-Fi 5, is also known as Very High Throughput, VHT Wi-Fi. So, HT control is the last field of the header, and after it is the frame body, which is the packet encapsulated within the 802.11 frame. And finally, there is the FCS, frame check sequence, in the trailer. Just like in an Ethernet frame, this is used to check for errors in the frame. And that's all for 802.11 frames. Remember, not all of these fields are present in all 802.11 messages. It all depends on the version of 802.11 being used and the message type. Like I said, these frames and their operations can be much more complicated than Ethernet frames. If you want to be an expert in wireless networks, you should definitely learn all the details, but that's enough for now. Next, before 802.11 message types, I want to introduce the 802.11 association process, which I only briefly mentioned in the last video. Access points are used to bridge traffic between wireless stations and other devices, for example, hosts connected to the wired network. But for a station to send traffic through the AP, it must be associated with the AP, and there is a process used to do that, to form that connection. There are 3 connection states. First, when the station is not authenticated or associated with the AP. Second, when the station is authenticated but not yet associated with the AP. And finally, when the station is authenticated and associated with the AP. The station must be authenticated and associated with the AP to send traffic through it. So let's look at a simple version of that process. First, the station sends a probe request message to learn about what APs and BSSs are available, and the AP sends a probe response to say that it is available. Note that there are actually 2 ways for a station to scan for a BSS. First is active scanning, where the station sends probe requests and listens for a probe response from an AP. That's what I show in the diagram on the left. But there is also passive scanning, in which the station listens for beacon messages from an AP. Beacons are sent periodically by APs to advertise the BSS. Okay, so using either active or passive scanning, the station knows about the AP and its BSS. However, it's still in that first connection state, not authenticated and not associated. Then there is an authentication exchange. For example, the station sends a password to the AP, and the AP authenticates it. If this is successful, we have reached the second state, authenticated but not yet associated. Finally, there is an association request and response. And if this is successful, we have reached the final connection state, authenticated and associated. Finally, the station can send traffic through the AP. Now, all of these messages, probe, beacon, authentication, and association, are the same type of 802.11 message. Let's look at the different types. There are 3 802.11 message types. First, there are management frames, which are used to manage the BSS. For example, the messages I introduced in the previous slide, beacon, probe, authentication, and association, are all management frames. There are more management messages than these, but I won't introduce them all. The second type is control. These frames are used to control access to the medium, the radio frequency. They assist with the delivery of management and data frames. For example, request to send and clear to send messages, which I very briefly mentioned in the previous video, are control messages. Also, ACK messages, used to acknowledge that a message was received, are control frames. The third type of message is data. These are the messages used to send actual data packets. Okay, here's a brief overview of the information we just covered. I can't say exactly which information you'll be tested on in the CCNA exam, but I think it's a good idea to have a basic understanding of these topics. Okay, let's move on to the next topic. First up, we are going to talk about different ways of using wireless access points. There are 3 main wireless AP deployment methods: autonomous, lightweight, and cloud-based. I'll introduce autonomous APs first. Autonomous APs are self-contained systems that don't rely on a WLC, wireless LAN controller. Hence the name autonomous, they are independent. And that means they are configured individually. They can be configured by console cable, remotely via Telnet or SSH, or also an HTTP or HTTPS web connection via a web browser GUI. For small networks, this is fine, but configuring APs individually in a large network quickly becomes unrealistic. Note that an IP address for remote management should be configured on the APs, so you can connect via Telnet SSH or HTTP to configure them. Radio frequency parameters, such as how much power it should use to transmit and which channel it should use, must be configured manually per AP. Security policies, for example ACLs, are also handled individually by each AP. Other settings such as QoS are also configured per AP. And there is no central monitoring or management of the APs. So, as I said before, each AP is its own self-contained system. Here's an example network with autonomous APs. When using autonomous APs, each AP should connect to the wired network with a trunk link. In this case, there are two SSIDs, so it might be obvious that a trunk connection is needed, because each SSID is mapped to a VLAN. But even if the AP provides only one SSID, the connection should be a trunk. Why is that? It's because the management traffic used to remotely connect to the wireless APs, as well as other devices, the switches, should be in a separate VLAN. I might not have mentioned this earlier in the course, but it's best practice to keep management traffic separate from regular data traffic by putting it in a separate subnet and VLAN. So there are trunk links between each of these switches carrying VLANs 10 and 20 for the wireless clients, as well as VLAN 99 for management traffic. When using autonomous APs, data traffic from wireless clients has a very direct path to the wired network, or to other wireless clients associated with the same AP. This statement might be a little unclear, but you'll understand it when you see the path that data takes when using a wireless LAN controller. So, with an autonomous AP, traffic between these PCs simply goes from PC to AP, among the switches, and then to the other AP and PC. Or between devices associated with the same AP, there's no need for the traffic to even go to the wired network. Soon you'll see how this is different compared to the traffic path when using a wireless LAN controller. Notice that each VLAN has to stretch across the entire local area network. This is considered a bad practice. Why is that? Why is it bad to have the same VLAN stretched across the whole network? Well, there are many reasons, but here are a few. First, large broadcast domains. Each VLAN is a broadcast domain, and if the VLANs are stretched across the whole network like this, each broadcast message will be flooded throughout the whole network. The second reason is that spanning tree will disable links. A big focus of modern network design is avoiding spanning tree as much as possible, because disabling links means a reduction in total bandwidth. Also, adding and deleting VLANs is very labor intensive, if it has to be done over dozens of switches in a large network. So, to summarize, autonomous APs can be used in small networks, but they are not viable in medium to large networks. A large network can have thousands of APs, and configuring and managing each of those APs one by one is not realistic. Finally, remember that autonomous APs can also function in the modes covered in the previous video: repeater, outdoor bridge, or workgroup bridge. Now let's talk about the next major deployment model for APs: lightweight APs. The functions of an AP can be split between the AP and a wireless LAN controller, WLC. The lightweight APs handle real-time operations like transmitting and receiving radio frequency traffic, encryption and decryption of traffic, sending out beacons and probes, etc. However, other functions are carried out by a WLC, for example RF management, security and QoS management, client authentication, client association and roaming management, etc. The WLC centrally controls all of these things for many lightweight APs. This is called split MAC architecture, split media access control, because the functions are split between the lightweight APs and the WLC. Note that the WLC is also used to centrally configure the lightweight APs. No more need to log into the CLI of each AP and manually configure them one by one. It's all done centrally from the WLC. Note that the WLC can be located in the same subnet and VLAN as the lightweight APs it manages, or in a different subnet and VLAN. I'll talk about different WLC deployments later. Note that the WLC and lightweight APs authenticate each other using digital certificates installed on each device. These certificates follow the X509 standard, which is the same that websites use to prove their authenticity over the internet. This ensures that only authorized APs can join the network, so an attacker can't make their AP join the network. Here's an example network, with a wireless LAN controller added this time. The WLC and lightweight APs use a protocol called CAPWAP, Control and Provisioning of Wireless Access Points, to communicate. CAPWAP is based on an older protocol called LWAPP, Lightweight Access Point Protocol. For communications, two tunnels are created between each AP and the WLC, like this. Note that each of those tunnels in the diagram represents two separate tunnels, each used for different purposes. So let's see what those two tunnels are. One is the control tunnel, and it uses UDP port 5246. There's another port number for you to remember. CAPWAP control tunnels use UDP port 5246. So this tunnel is used to configure the APs and control and manage their operations. Note that all traffic in this tunnel is encrypted by default, so it is secure. The second tunnel is the data tunnel, using UDP port 5247. All traffic from wireless clients is sent through this tunnel to the WLC. It does not go directly to the wired network, or even directly to another client associated with the same AP. It must go through the tunnel to the WLC first. Now, of course, in reality, the traffic does pass through the wired network to go to the WLC. However, it is encapsulated with new headers to form the tunnel, just like I showed with GRE and IPsec tunnels in the WAN video. Note that traffic in this tunnel is not encrypted by default, but you can configure it to be encrypted using a protocol called DTLS, Datagram Transport Layer Security. I mentioned TLS, Transport Layer Security, briefly in the WAN video. DTLS is basically the same thing, but it uses UDP, whereas regular TLS uses TCP. Now here's another difference between lightweight and autonomous APs. Because all traffic from wireless clients is tunneled to the WLC with CAPWAP, APs connect to switch access ports, not trunk ports. You could make a trunk link if you want, but there's no need for multiple VLANs to cross that link. To make that clear, let me demonstrate the traffic flow when using split MAC architecture. Okay, I've simplified the diagrams. On the left we have a split MAC architecture, with a lightweight AP and a WLC. On the right we have an autonomous AP architecture, sometimes called a local MAC architecture. As you know, when using autonomous APs, they must connect to the network with a trunk link. There should be a VLAN for each SSID the AP offers, as well as a VLAN for network device management. If a wireless client wants to send traffic out to an external network, it sends the frame to its wireless access point, which then forwards it to the default gateway over the wired network, which will then forward it according to its routing table. And if a client wants to send traffic to another device associated with the same AP, the traffic has no need to enter the wired network. The frame is sent to the AP and then simply forwarded to the destination. When using a split MAC architecture, this is all very different. As I said before, the AP doesn't have to connect to the switch with a trunk. An access link is fine. However, a trunk link is needed to connect the WLC to the wired network. In this case, instead of the AP mapping each SSID to a VLAN and forming the border between the wired and wireless network, the WLC takes that role. Traffic from a wireless client is sent to the AP and then tunneled to the WLC. Then the WLC sends it over the wired network to the default gateway, which will forward it as appropriate. Even if the traffic is destined for a host associated with the same AP, it is first tunneled to the WLC and then tunneled back and sent to the destination. Okay, hopefully that helped demonstrate the differences between the traffic paths used by each of the two architectures. There are some key benefits to using a split MAC architecture. This isn't a complete list, and you don't have to memorize it, but you should be aware of what benefits are provided. First, scalability. With a WLC, or even multiple WLCs in large networks, it's much simpler to build and support a network with thousands of APs. That would simply not be feasible with autonomous APs. WLCs also provide dynamic channel assignment. The WLC can automatically select which channel each AP should use, so you don't have to manually plan which channel each will use. The WLC can also automatically set the appropriate transmit power for each AP to provide sufficient coverage without interfering with other APs. The WLC can also provide self-healing wireless coverage. So when an AP stops functioning, the WLC can increase the transmit power of nearby APs to avoid coverage holes. Seamless roaming is also provided, so clients can roam between APs with no noticeable delay. Another benefit is client load balancing. So if a client is in range of 2 APs, the WLC can associate the client with the least used AP to balance the load among APs. And the last benefit I'll mention is security and QoS management. Central management of security and QoS policies ensures consistency across the network. As I said, you don't have to memorize this list, but definitely be aware that the split MAC architecture offers various benefits. Now, just as autonomous APs can function as repeaters, outdoor bridges, etc., lightweight APs have different modes as well. First is local mode. This is the default mode where the AP offers a BSS, or multiple BSSs, for clients to associate with. So this is the standard operational mode of an AP. Next is Flex Connect mode. In this mode, the AP also offers one or more BSSs for clients to associate with, but it adds extra functionality. It allows the AP to locally switch to locally forward traffic between the wired and wireless networks if the tunnels to the WLC go down. So here on the left are some standard traffic paths used with lightweight APs. All traffic is tunneled to the WLC first. But what if connectivity to the WLC is lost, causing the tunnels to go down? That's not a problem if Flex Connect is enabled, because the AP can start forwarding the frames locally like an autonomous AP. No need to tunnel the traffic to the WLC. Okay, that's Flex Connect mode. The next mode is Sniffer mode. In this mode, the AP does not offer a BSS for clients. Instead, it is dedicated to capturing 802.11 frames and sending them to a device running software such as Wireshark. So it listens to wireless traffic, and then sends those packets to packet capture software for analysis. The next mode is Monitor mode. Again, it doesn't offer a BSS for clients. Instead, it is dedicated to receiving 802.11 frames to detect rogue devices. If a client is found to be a rogue device, an AP can send deauthentication messages to disassociate the rogue device from the AP. The next mode, Rogue Detector mode, is similar but different in a key way. In this mode, the AP does not even use its radio. Instead, it listens to traffic on the wired network only, but it receives a list of suspected rogue clients and AP MAC addresses from the WLC. By listening to ARP messages on the wired network and correlating it with the information it receives from the WLC, it can detect rogue devices. Okay, next is yet another mode that does not offer a BSS for clients. That is SE Connect, or Spectrum Expert Connect. In this mode, the AP is dedicated to RF spectrum analysis on all channels. It can send information to software such as Cisco Spectrum Expert on a PC to collect and analyze the data. This can help find sources of interference. Okay, the next mode is Bridge Mesh mode. Like the autonomous AP's outdoor bridge mode, the lightweight AP can be a dedicated bridge between sites, even over long distances. A mesh can also be made between the access points. Here's an example similar to what we saw in the previous video, APs connecting sites together. And here's an example that looks more like a mesh, again, connecting sites together over potentially long distances. Now there's one more mode, that is Flex plus Bridge, which basically adds Flex Connect functionality to the Bridge Mesh mode. This allows wireless access points to locally forward traffic, even if connectivity to the WLC is lost. Here's that complete list. This is a lot of different modes, and we only very briefly looked at each one, but that's okay. If you want to know more about any of these modes, Cisco has documentation about each of them, and you can find it with a Google search. But for the CCNA exam, you should just be able to identify the basic purpose of each of these modes. I don't recommend memorizing this list. Just understand the basic purpose of each. Now let's look at the last main type of AP architecture, cloud-based. Cloud-based AP architecture is in between autonomous AP and split MAC architecture in terms of how it functions. Basically, it involves autonomous APs that are centrally managed in the cloud. An example is Cisco Meraki, and because the CCNA is a Cisco exam, that's probably the one you should be aware of for the CCNA. The Meraki dashboard, which is a website you log into, can be used to configure APs, monitor the network, generate performance reports, etc. Just like I mentioned for WLCs, Meraki also tells each AP which channel to use, what transmit power to use, etc. However, regular data traffic is not sent to the cloud. It is sent directly to the wired network, like when using autonomous APs. So, only what we call management traffic or control traffic is sent to the cloud. Let's see an example. Information such as RF spectrum information and management information is sent to servers in the Meraki cloud. But regular data traffic, such as two PCs communicating with each other, is direct, and there is no need for it to be sent to the cloud. So I think you can see how the functionality is in between autonomous and lightweight APs. Here's an image from Meraki demonstrating the same concept. Notice that the Meraki management data, the green arrow, is sent to the Meraki cloud. However, user data, so regular traffic, is sent directly to its intended destination, such as a web server or a file server. Here's another image from that same Meraki webpage, giving a look at the Meraki dashboard. This is where you monitor the wireless network, make configuration changes to APs, etc. I use the Cisco Meraki solution in my job, and I really like it. It's easy to use and set up, and the Meraki dashboard makes it easy to monitor the wireless network and make changes as needed. Okay, that's all for the cloud-based architecture. Like I said, it's halfway between autonomous AP and split MAC architecture. Autonomous APs that are centrally managed. The final topic for today is WLC deployment models. Since we're talking about wireless LAN controllers, this applies to split MAC architecture only, not autonomous AP or cloud-based AP architectures. There are 4 main WLC deployment models, 4 ways to deploy a WLC in your network. I'll show each one with a diagram, but let's summarize them first. First, a unified WLC deployment. The WLC is a hardware appliance, a separate hardware device, in a central location of the network. Then there is the cloud-based WLC deployment. The WLC is a VM running on a server, usually in a private cloud in a data center. Keep in mind that this is not the same as the cloud-based AP architecture we just discussed. In this case, the APs are not cloud-based, they are lightweight APs. The cloud-based name here simply refers to where the WLC is. In an embedded WLC deployment, the WLC is integrated in a switch in the network. And finally, in a Cisco Mobility Express deployment, the WLC functionality is actually integrated within one or more of the APs in the network. So here's an example of a unified WLC, a separate device, a separate hardware appliance, that is deployed in a central location of the network. A unified WLC can support up to about 6,000 APs, and if you need more than that, you can add additional WLCs. This kind of deployment is suitable for a large enterprise campus. Here's a photo of some different Cisco WLC models. Of course, the larger models are more powerful and can support more APs than the smaller ones. Next is the cloud-based WLC. In this case, the WLC is a VM running on a server, typically in a private cloud in a data center. This kind of WLC can typically support up to about 3,000 APs, and again, if more are needed, you can add more WLC VMs. I'd like to repeat here that a split MAC architecture with a cloud-based WLC is different than the cloud-based AP deployment we looked at earlier. These are lightweight APs, and cloud-based just refers to where the WLC is. Next, embedded WLCs. In this case, the WLC is embedded within a switch. This type of WLC can support up to about 200 APs, and if you need more, you'll have to add more switches with embedded WLCs. Embedded WLCs are suitable for smaller campuses. Finally, Cisco Mobility Express places the WLC within an AP. The AP containing the WLC builds internal CAPWAP tunnels to it, and the other APs do too. A Mobility Express WLC can support up to about 100 APs, and you'll have to add more APs with embedded Mobility Express WLCs to support more APs. This kind of deployment is suitable for a small branch office. Here's that summary of the different WLC deployment models, and I've added information about how many APs can be supported by each. Definitely be familiar with these 4 deployment types for the exam. Okay, here's what we covered in this video. We started with a brief introduction to some different kinds of 802.11 messages, and the frame format used by 802.11 wireless frames. Because wireless networks have different requirements than wired networks, there are quite a few differences between 802.3 Ethernet frames and 802.11 wireless frames. We then covered the 3 main kinds of APs: autonomous, lightweight, and cloud-based. Make sure you know the basic characteristics of each and are able to compare them. Finally, we looked at the different wireless LAN controller deployment options to be used with lightweight APs. Make sure to watch until the end of the quiz for a bonus practice question from Boson Software's ExSim for CCNA. Okay, let's go to quiz question 1. What kind of message is an 802.11 probe request? Pause the video now to select the best answer. Okay, the answer is C, management. Here are those 802.11 message types we covered earlier, with a few examples of each. Okay, let's go to question 2. Which of the following AP types are centrally managed? Pause the video now to select the best answer. Select 2. Okay, the answers are C, lightweight, and D, cloud-based. Lightweight APs are centrally managed by a wireless LAN controller, and cloud-based APs are centrally managed by a cloud server such as Cisco Meraki. Okay, let's go to question 3. Which of the following AP types uses the CAPWAP protocol? Pause the video now to select the best answer. Okay, the answer is C, lightweight. Lightweight APs use CAPWAP to communicate with the WLC via 2 tunnels, a control tunnel and a data tunnel. Okay, let's go to question 4. Which of the following lightweight AP modes offer a BSS for clients? Pause the video to select the best answers. Select 2. Okay, the answers are A, local, and C, Flex Connect. Local is the default standard operating mode. Flex Connect offers the additional ability to continue forwarding data traffic locally, even if the tunnels to the WLC go down. Okay, let's go to question 5. Which of the following WLC deployments supports the greatest number of APs? Pause the video now to select the best answer. Okay, the answer is D, unified. Embedded WLCs support about 200 APs, cloud-based about 3,000, Mobility Express about 100, and unified about 6,000. Okay, that's all for the quiz. Now let's take a look at a bonus practice question from Boson Software's ExSim for CCNA. Okay, here's today's Boson ExSim practice question. Here it is. Select the 802.11 MAC frame components and drag them to their appropriate position within the 802.11 MAC frame format. Use all descriptors. Okay, so these are some different fields of an 802.11 MAC frame. Now, these are not all of the fields that I introduced in this video. Specifically, the QoS control and HT control fields are missing. However, like I said, depending on the version of Wi-Fi being used, as well as the message type, not all of these fields might be present in any given 802.11 frame. So just take these ones and put them in the correct order. Okay, hopefully it did that. Let's walk through it. I won't go from beginning to end, but I'll start here with the FCS, frame check sequence. That is the only field in the, not the header, but in the trailer. And that comes right before, or sorry, not right before, right after the data. So this is the encapsulated IP packet, the frame body. Okay, so let's go back to the beginning. Which field comes first? That is the frame control field, which provides information such as the message type. And then after that is the duration field, which in some cases can be an ID field. And then right after that, we have three addresses, address 1, 2, and 3. Again, not all of these might be present in any given 802.11 MAC frame. And after address 3, we have the sequence, and then address 4. Again, this one might not be here depending on the message type. Now, the frame format that I introduced in this video will have QoS control and HT control here between address 4 and the data, but they are not present in this question. Okay, I'll click Done, and then Show Answer, and that was correct. So here is Boson's explanation. I recommend pausing the video now to read it. And I'll scroll down a bit more. Okay, there it is. And there are some references both to Boson's own curriculum and some other documents on the internet. Okay, so that was a quick look at Boson Software's ExSim for CCNA. As I've said before, these are by far the best practice exams for the CCNA. If you want to get Boson ExSim, please follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There won't be a lab for this video. Again, we didn't cover any configurations in this video. We are still laying the foundational knowledge that you will need. Wireless LAN configuration will be its own separate day of the course. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to Benji, Kwa, Ricardo, Safet, Mason, Andre, Apogee, Mir, Petrosius, Dragos, Tanvir, Gerard, Tom, Martin, Tebogo, Pavel, Abraham, Sergey, Njoku, Victor, Suki, Kenneth, Seamus, Marcel, Coney, Donald, Gustavo, Prakash, Nasir, Erlison, Marco, Ed, John, Funny Dart, Velva Jacob, Boson Software, Devin, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. This is the list of JCNP level members at the time of recording, by the way, August 29th, 2021. If you signed up recently and your name isn't on here, don't worry, you'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.